So not sure how big the class size will be. My preference would be to actually have a fairly small class. But for today's lecture, I wanted to cover a set of basic introductions to the course topic, and give an overview of what we're covering within the course, talk some of what's expected from you, a little bit about marking, that sort of thing. I then wanted to go on to discuss some of the motivations for why we teach this material, why those from diverse backgrounds might be interested in the sort of topics covered here. So the class objectives here are listed as follows. And, the class is aimed to help students from a variety of backgrounds. This is a computer science course, but it's aimed at students from across campus. And it's designed to help students appreciate and critique simulation models applied to whatever area of activity they're interested in, to understand proper limitations of those models, and strengths and weaknesses fundamentally. Gain familiarity with specific modeling software. It's hard to get an appreciation for the concepts, material in the course, without actually applying it. And so, of necessity, there's exposure needed to specific modeling software. We have two that we're going to be using in the term, Vensim and AnyLogic, but they're not particularly privileged in this regard. A very important sort of outcome will be to learn to conceptualize, formulate, analyze, and assess, test, and use simulation models. So the idea here is we're building models that can inform decision making, and in order to build models that are robust, that are resilient under slight variations of your assumptions, that will carry weight in terms of their recommendations and so on. It's important that they be built in a principled fashion, and we're going to be talking about stages of that process here. So model conceptualization, the formulation of models, being sort of getting into some of the nitty-gritty, and analyzing the models. Come on in. Sure. So the hope will be by the end of the course you'll be familiar with elements of each of those, predominantly through projects. And the final thing is to understand and appreciate some open areas of modeling research. There's going to be, what we're talking about within this course gets into some really cutting edge stuff. Stuff where it's full scope of application, the proper means in which it's applied, our understanding of that is still evolving, still being refined. And there's some really important open areas, things which have not been well addressed, or which are sort of open questions, areas for research that we're working on, other groups worldwide, as to how best to use the tools of dynamic modeling, models that help us simulate a system over time, how to use it most effectively in particular contexts, how to combine multiple modeling types most effectively so they complement each other's strengths and weaknesses, etc. So these are some of the objectives of the course. This is not an armchair course. It's not a course where you'll learn a bunch of concepts and simply have a conceptual grasp of it. It's a course which will require, as an integral part of our meetings here, and I'll get to that in a few minutes, close work together on advancing projects, advancing through exercises that will challenge you, etc. So it is a course which is going to involve a lot of hands-on contact with material. So some objectives. These are some of the, please come on, some of the topics that are being covered within the talk, within this course. First of them are listed here, and that's motivations for the course. We're going to be talking about that today as time allows, probably bleeding over into the next session. What's the motivation for these techniques we're presenting? Where do they fit in the traditional toolbox of techniques that may be used to address similar questions. Why is it that they're viewed as being so keenly needed, particularly in certain domains? We're going to be talking about certain system science concepts. These range from notions of emergence, notions like nonlinearity, and trying to illustrate them in specific ways, and also some concepts related to describing how a system evolves over time from different perspectives. So there's a notion of phase space, for example. There's notions of complexity as applied to dynamics that will come in. Now, there's a set of techniques that are also germane to this sort of modeling that are more qualitative in character. Okay? They involve not simulation yet, but attempts to characterize the behavior, characterize the structure, and by extension, behavior of a system in more qualitative ways. Okay? So the idea here is that I'll introduce you to some techniques, particularly drawn from what's called the system dynamics method, which allow you to take a description of some problem that you're interested in and systematically create a diagram that illustrates some of the relevant structure in a way that will give insight into possible behaviors and potentially insight into where you could change things most effectively. So the idea is to go from a sort of qualitative understanding that's in your head, a so-called mental model, and put it into a form that at least it can be shared, critiqued, refined, and evolved, and that would allow for some pretty good sense as to some of the behaviors that might be expected from it, and some anticipation of where to intervene. So there's going to be a toolbox of types of modeling we're going to be seeing, and this is a more qualitative one. It's an extremely useful technique to apply, particularly when there's limited data available or limited understanding. You can still actually gain some very significant insights from a structured diagram, even though it captures predominantly qualitative concepts. So we'll be talking about that, and we'll talk a little bit about how that can be used in a group context to do what's called group model building. This is a technique used when there's multiple stakeholders, multiple people who are interested in some system, maybe because they're part of it, they're interested in change to the welfare system in the state, so they're interested in improving the responsiveness of a software company's handling of customer support requests or what have you. And by getting them together using these sort of techniques, you can actually sometimes get a lot of benefits in terms of understanding of how to go forward, how the different parties work together most effectively, breaking down stereotypes on both sides so that they understand the different ways in which their actions affect one another, and therefore are less likely to view others as kind of in tension with themselves. There's three sorts of modeling that we're going to be looking at in brief glimpses during this term. We're going to spend most of our time on two types. The three types of modeling are a technique known as system dynamics. This is a technique which traditionally involves some aspects of qualitative, some aspects of quantitative. It in fact relates to differential equations. It can be unpacked, certain quantitative diagrams can be unpacked into differential equations on the quantitative side, but it has a very important qualitative side as well. So system dynamics modeling, feedback-centric modeling that puts a really strong emphasis on changing how people think about a system and how people cooperate together most effectively. We're going to be talking about agent-based modeling, which is a more recent technique that's achieved a great amount of interest because of its capacity to represent behavior at multiple scales, time scales, but also spatial scales. So you might represent people in a neighborhood, and neighborhoods located within cities and regions, and you have behavior playing out at each of those scales that's distinctive. Okay? And you have interventions that can intervene at different scales. It also can capture network effects really well, spatial embedding, nesting of different contexts, I guess I mentioned, but also agent histories and interventions, policies that might depend on particular agent histories in a way you really can't capture effectively with system dynamics. But it can be, turns out, hybridized with system dynamics in very powerful ways. And the final type of modeling that we'll talk about, well, in class we're going to look at it more briefly, but some of you may want to do projects which involve it more centrally, and I'll be here to facilitate those for many class sessions, in fact. And that is what's called discrete event modeling. It's a type of process-centric modeling where we have a set of things that are called at an abstract level entities. They may be people flowing into a hospital seeking treatment. They may be pedestrians trying to go into a subway system to take a train. They may be cars on a road. They may be cars in an assembly factory. They may be widgets being produced in another factory. Here we have a set of these things flowing through a system, and it's a very process-centric modeling in the sense that you're asking where are the bottlenecks, what processes, so what steps in assembling that car, or getting the people through the turnstiles, or handling which patients should be seen first in a hospital. Which of those are the bottlenecks? Which amount of resources would help facilitate that process most effectively? So this is, it says discrete dynamics. That should be discrete event dynamics. Here we're talking about things that are called as part of discrete event modeling. Okay, those are the three major sorts we're going to be talking about. Stocks and flows are part of system dynamics, and they also form a very useful way to think about systems regardless of which of the three techniques we used. We're going to be talking about ways of hybridizing these techniques. This is really getting edge. There's not many people able to do this or doing it. Unfortunately, the software we'll be using will allow us to do this quite easily. Software, in this case, being AnyLogic, and really combining these techniques. So you could have people in a population that present for care in a hospital, and if they secure proper care, they'll go back to the population soon. If their care is poor, they may go back to the population but re-present quickly, and they have histories and biographies associated with each agent. So hybrid modeling would be some of the components we talked about. We're going to be talking about also modeling what we've termed dynamically complex decision problems. This is a problem which involves not just dynamics over time in a very complex way, but uncertainty concerning certain factors that affect that system. So an example might be if you're the city of Calgary, for that matter the city of Saskatoon, and you're interested in planning your infrastructure. Do you build a rail line here in Saskatoon? In Calgary, do you expand the existing rail line? What sort of roads do you put in place? Do you start planning for North Bridge, for example, here in town? That decision is tied up with a lot of factors that aren't under your control. Examples would be how the economy proceeds. What are oil prices? What are commodity prices, etc. And we're going to be talking about problems that combine multiple elements of that sort of uncertainty and these simulation models in a powerful way. The idea will be here, you need to be able to make decisions in an adaptive way. An example of this is how decision making is undertaken here in town by the health region with respect to a disease called West Nile fever and the infection associated with it, West Nile virus. Has anyone heard of West Nile here? Yeah. So can you say anything about West Nile? What's it associated with? How is it transmitted? Is it by needles or? It's mosquitoes. It's mosquitoes. And you folks have been around here for a couple of years. You'll know that mosquito population is variable. Some years it's really bad. This year it's really bad until recently. And other years it's not too bad. Now, they could have the same plan in place every year, regardless of what the mosquito populations. But it would be kind of foolhardy. Foolhardy because if it's not a bad year for mosquitoes, you don't need to spend a lot of money, doing source reduction, spraying, and so on. If it's a really, really bad year, you want to put in extra effort to control the population of mosquitoes, or to issue safeguards for people to be careful when they go out. And you see those sort of things in the paper. Those things cost money when they're in the form of public service announcements, etc., to be played on the radio. Now, the city of Saskatoon here, on a week-by-week basis, has to examine whether or not they're going to launch an advisory, whether or not they're going to trigger a spraying campaign or source reduction campaign. Week by week, they watch the temperature, because the temperature affects the mosquitoes. They watch how many mosquitoes there are in the first place. They watch the fraction of those mosquitoes that are infected, and they make their decisions over time. So we're going to be talking about techniques that allow us to do that in the context of uncertainties like temperature or amount of rainfall that affect the things we care about, mosquitoes and biting and risk to humans. So there's going to be some dynamic decision problems we're going to take a look at as time allows. We're going to spend a fair bit of time on agent-based modeling and talk about the environments agents can be in. So we're going to look at two types of environments. These agents in a model, think of them as people in a spatial environment, or deer. So I'm involved with a deer model, assuming that a mule deer over Saskatchewan, and they move around in the environment from brush to go down to the river to drink and that sort of thing. Here we have some environments that may be irregular, irregular geometries where they move around in, and the nature of that environment affects them. The fact that there's a river there means they go in certain paths of the river, and it turns out that's important because they shed this thing called prion, which is really ineffective and can spread to other deer. So the fact that they travel in certain paths is important. So capturing that sort of geometry could be important for understanding how the disease spread, but also where you could intervene. If you could build a fence, or if you could attract them to different places through providing food or what have you, where should you provide that food? If you could drop vaccination food in certain places, where would be the quickest place to disseminate it? So capturing in space, but also networks. So we're going to talk about multiple types of networks and the ways in which they impact things. Networks, there's a whole area called network science, which has kind of cropped up in the past decade or so. And within the network science area, people have realized that when you have entities of various sorts, agents, you could think of them, and that can be described in networks, the structure of those networks are really, really important for understanding what's happening over time often, and also for trying to change that. For example, give me some examples of networks that might be around. We have computer networks for sure, and many of you from computer science background might go instinctively to think about that, and I'll throw that out there as just one sort of network. I'm talking about networks broadly. What can we conceptualize? What sort of situations might we think of ourselves as being in a network of sorts, ourselves, say, for people to start with? Sorry? Family, yeah, excellent. So family, a social network, right? In the movie. So family, friends, for example, business colleagues if you're out working, fellow graduate students. These are all, you can think of them as different networks, and they all can be viewed as part of a broader social network. So those are good examples of networks. Now there's others that can transmit disease more easily. Give me an example of a type of network which might transmit an infection. Sorry? So an epidemic might be caused over what sort of network? What sort of network might lead me to get infected really easily if I do what with someone? That's the key thing. If I, for example, share a needle with them, or if I have some sort of close, intimate interaction with them, if I share food with them, for example, these things might, for example, transmit pathogen disease. but just being proximate to someone, close to someone, might be a risk for transmitting flu, something like that. It might be also that I influence people. So, you know, that I influence people nearby me. There's very good evidence for that. So ideas spread via networks. Innovation spread via networks. We talked about networks for people. Proximity networks. Networks based on needle sharing. Networks based on sexual connections. Whatever. Friendships. What other sorts of... Give me another thing that could be in a network. Good. Company and brands. Excellent. Excellent. So companies have links to suppliers, right? And they have links to people who distribute their own, the things they produce. So maybe they produce an iPhone, and there's Apple stores all around, sort of retail outlets that sell them. They have a network of those, right? But they have certain suppliers who supply the case, or they supply the display for that. So that's a good example. Companies can be in networks. Organizations can be in networks. Universities can be in networks. People want to take this course from Queens, and I found out that there's a network of Canadian universities that allows them to do that. If you look at a map of Canada, what do you see? You see a network of cities. Cities with connections that are maybe rail connections or road connections. Networks are all around us. They have to do with topology. Who's connected with whom? They have to do with relational aspects. I do the X does this with Y. There's a relation between them. It's not just X in isolation. It's not just Y in isolation. There's some relationship between them as an attribute that's important. So we talked about how we can capture these things with models. And it turns out that a portion of the software can make this quite easy for certain kinds of networks. And it can be very powerful. We talked about debugging models, calibrating, parameterizing. Probably won't spend much time in dimensional analysis other than to sort of keep yourself from making mistakes there. Some best practices in model building and some of the trade-offs. Now, this class is going to be a little bit odd. This particular session is an unusual session. Standing up here talking a lot more than I will be normally. Be very adapted to student project and project base. It'll be fairly demanding in terms of stretching yourself, and some in terms of time, and I'll talk about that in just a minute. It will be interdisciplinary. Could each person go around and say, what program are you in, or what's your home department if you prefer? Just to give some idea and to speak to this issue. So you're from which department? Computer science? Okay. So we have someone from Community Health and Epi who's expressed an interest in coming, so I'm not sure about that. And also someone from Johnson Shoyama School who's also expressed interest, so I'm not quite sure where we're at there. There's another guy from physics background who's recently started in computer science. We are dealing here with people from interdisciplinary backgrounds. We'll see how that evolves in terms of others, and maybe even more richly so. What this means is I'm aiming this material to be accessible by a broad set of people, and I'm going to be answering questions that speak to different backgrounds and levels of education. For example, I've done a fair bit of biomedical type work in terms of simulating immune system behavior, working with models of diabetic metabolism and so on. And so I might address some things at that level at times. At other times, talk about some issues from a computer science perspective. And I'd ask people to be patient in me dealing with this. It also means we're aiming for teams that will complement each other's strengths when it comes to projects. And I'll come back to that in a minute. The biggest change, though, ladies and gentlemen, for this term, from previous, so I've been running this course for this kind of similar form for about 6 years, 7 years, something, 5 years maybe, in its current form. It's been very successful. We've had students from all around campus taking it. and it's been very good. However, this year we're going to have a major innovation that was stimulated by highly successful experience I had in teaching a summer school this year, and from a lot of discussions and preparations in previous events and classes leading up to this. The idea is this notion of flipping the classroom. Okay, and this is going to be a central feature of this course. It may make the course different from any other course you've ever taken, not only in terms of content, but in terms of how it's delivered. Hopefully in a good way. So a key component of this is this notion of inverting the classroom or flipping the classroom. The phrase that's used for this sometimes, and I have to apologize, it's kind of a little bit of a truism, but it's the idea is the professor goes from being the sage on the stage up here, strutting around and talking to you, giving lectures, etc., in a fixed way, to being the guide on the side, someone who's working along with you, helping look over your shoulder, see what you're having trouble with, addressing your questions, helping to advance your understanding by addressing your specific challenges that you're struggling with, or things you're grappling with in terms of projects or with exercises, etc. Okay? So the idea is to use the classroom experience to its strength. How many people here have ever seen the Khan Academy site? Okay, one person. There's a profusion online right now of electronic materials to support teaching. Khan Academy is a great example because it has these short little snippets of kind of topics, particular topics. I'm trying to do that for a lot of material here. But there's also a whole move towards what are called massive online open courses, MOOCs. Okay, Coursera, edX, the MIT, Harvard Initiative, Stanford is a large one. And the basic gist is, I have literally hundreds of videos that relate to subjects in this course. Probably upwards of 200 now related specifically to this course. There's some additional ones I have. I could come here and I could give the same talks again, but really that's not exploiting our time together well enough, because you can go to YouTube and you can play a video where I've explained this, probably with more detail than I'm going to be able to fit into this class. And you can, in fact, go to 3 lectures for some topics and see me explain in 3 different ways, with different examples and stuff like that. For me to sort of do the same thing here doesn't seem to me the best use of our time. Doesn't seem the best use of your time. What I can do is, and what I'm asking you to do for this course, is to review selected materials. I'll point you to videos for each course, each class, each particular session of the class, where I'd say, I'd like you to watch this video. Okay? Watch this video, and I want you to go along with it. So I want you to do the exercises as I do them in the video. And it's going to be me going through some little exercise, some of it, and sometimes talk about things up to the church. So you come to the course, you come to a session of this course with some understanding in mind of what we'll be covering. And hopefully, and this is the key thing, hopefully with questions, things you didn't get, things you don't understand how it applies to what you care about, barriers that you couldn't get right when you were following the exercise, questions of the generality, could you use it for this other thing? Now, you could be doing projects as well in the context of those courses. That is going to be a required component of the course. Each person, either in a group or on an individual level, is going to work on a project. And the goal will be to leverage these online materials in a way that will inform also your projects. And so you may ask, well, for my project, I have this thing I'm trying to do. Maybe I'm trying to simulate the, performance of servers. I'm trying to understand the dynamics of cell signaling at the biomedical level, or I'm trying to understand the ways in which this innovation spreads in the industrial sector for the person from Vensim. These are questions that I can address in class by sort of meeting and giving an impromptu discussion of how we capture that sort of thing. So the goal here is to use class time for the things that it alone can provide. A chance for us to meet up, a chance for us to look at what you're having problems with and to address your particular questions, and for me to talk some about more advanced examples that might illustrate some of your needs, war stories from past modeling projects. These sort of tools I've been working on for years. I started doing this sort of modeling almost 25 years ago now, and I've used it in all sorts of different contexts, industries, municipal governments, national governments, companies, wide range of different clienteles. And the issue here will be to try to leverage some of that experience with you in a way that will speak to your interests. So this is very different. I am not anticipating being here giving a full lecture. Now, depending on how this goes, I may give a synopsis. I may walk through the essentials from what's being talked about. I may highlight the most important points from this lecture that I see it. But I'm asking you, requiring that you make a good faith effort to try to review the materials. And if you don't get a chance, you can ask me, could I give a synopsis in 15 minutes of overview it, and then we'll deal with the questions as they come up from you. But we have a huge opportunity here. We have an opportunity to do something remarkable in the course of the semester. So I used this in August in a boot camp that I taught here on campus for people from around the world. It's related to the course materials. And they were able to accomplish amazing things in the course of 1 week in terms of building models. The goal is to do something similar, so that we all come out of this class with really viable projects. Projects that are workable, that address real interests from your part, and where there's been learning that went on by doing, rather than just in a formulaic way by hearing my lecture and kind of thinking about it. Okay? So that's the goal here. That's not necessarily for everyone. Some people may feel, you don't want to sort of get involved in a project and so on, and that's fine. But it will be a very important part of this semester, and you may want to, to look elsewhere. So we'll be using a flipped classroom, and I will give some talks. And if you have a particular question, I may give a mini lecture on that. If there's some topic which comes up, and I realize I didn't cover that in a way that I should have in the video, I may talk about that. But a lot of it will be spent me going over and meeting with small groups. Sometimes we'll break and we'll even go to separate rooms around here, and I'll go from room to room and help facilitate things. That's the goal, okay? And the goal is to use me to advance your projects in a way you wouldn't be able to on your own, and to address those questions. So, any question about this model? Has anyone participated in a flipped classroom before? We're getting to be popular in some areas, and there's a number of initiatives around campus here to apply to a similar model. There's a whole theory behind it. So, questions about that? Okay. Okay, so the class won't be for everyone. I've put some things up here, and in light of the people here, I probably should have a separate one for those for biomedical engineering as well. Traditionally, people from a variety of backgrounds have come to this course, and as I've noted, that affects my presentation style. It changes what I present, the level at which I present it. Sometimes I will break out and have tutorials for those from certain backgrounds to get them up to speed with certain things. For example, students not from computer science will probably be new to Java, maybe new to Java, in which case I have a set of Java tutorials, and I can meet with the student and walk them through how references work, or what a method is, and what an object is, what a class is, if necessary. I'm glad to do those sort of things, but not in a way that will take everyone's time to address those students. So here we'll be demanding different things on the part of different people. Most of the people here sound like they're from a fairly quantitative background, but you know, from a computer science standpoint, what we're talking about here is often not directly covered in computer science books. We're talking about characterizing phenomena out there using tools from computer science. We're talking about understanding how things work in the world so that often we can make better decisions about the better choices, more effective decisions without blowback, without a lot of unexpected effects. And computer science provides us a bunch of tools, but most classes in computer science don't have to deal with that characterize, describing this. Even computer systems, there's an art to how do we characterize a computer system so that we can simulate its behavior under all sorts of different loads without actually going and buying the hardware, you know, buying or renting the virtual machine time or what have you. So computer science is going to be patience. It's needed, you know, to learn how to sort of characterize things. And I will sometimes be using health science concepts and terminology because, first of all, I do a lot of work there, and I think it's a great example of provides great examples of how this sort of stuff is applied. People from other backgrounds, there's going to be a fair number of computer challenges. On some parts of it, like the system dynamics modeling, it's actually not, it doesn't require programming in a traditional sense. It's something which requires facility with computers, but not programming in a classic sense. It's so-called declarative language. In other words, lets you describe the what and less of the how. By contrast, once you get into any logic, and specifically agent-based modeling, there's going to be some need to deal with Java. Some need to sort of wrestle with some aspects of Java, because it underpins the framework and makes it extremely flexible. So we're going to be talking about that. While I'm going to be having a domain focus that tilts towards health here, I'm going to be making effort to try to give examples from other areas. So I'll talk about examples from computer systems, behavior from computer systems that's sometimes unexpected. You know, why do servers behave for a wide range of performance, a wide range of sort of hit rates pretty well, and then suddenly degrade, for example. What sort of behavior is associated with network congestion, that sort of stuff. I'll sometimes appeal to things like that. Sometimes they'll talk about things on the business side, talk about business issues. Sometimes they'll talk about things at the biomedical level, so things having to do with dynamics within a cell or within an organ system or what have you. You have to realize that what we're talking about here, it may be applied, maybe examples are given that are illustrative in a certain area, but applies to a wide variety of areas. It applies to area after area after area. And that's why these modeling tools are so powerful, because they can speak to problem solving in a wide variety of areas. Okay. There will be some pushing involved, and I'm not trying to sell the class to anyone. It's just trying to help people understand what's required. Well, I mentioned class diversity, and we'll see how that evolves. Okay. Here's some resources from students. So arguably the most important resource, one of the most important resources certainly, is a set of videos that I have that, actually this is sort of a gateway to a whole set of materials. Okay? So it's tinyurl.com/consensusabm. Okay, and so that's CONSENSUSABM. This URL will get you to a web page where I've been collecting videos related to this course. And also model libraries, example models, also tutorials on Java, tutorials on particular models, tutorials on particular topics like health economics, and how those work with models. So there's all these online videos. Now, I have a YouTube channel which you can go to, which provides these videos and quite a few more as well. And has playlists associated with particular topics, so you might want to look at that as well. But this is a good starting point for many of my videos, and it gives sort of preferred videos for certain topics. Okay, so that's one resource. Second resource is office hours. I'm going to be holding office hours, and they're in the syllabus, I think, but fundamentally I'm going to be holding meeting times for students right after this course on both days. It's offered Tuesday, Thursday. So if students want to meet after a convenient time, especially because people come from across campus, I figured abutting the office hours with the course, having them adjacent, would be easiest for everyone. So I'm going to have them right after the course. If you want to meet with me other times, great. I'm happy to do so. Just write me. Okay. I do teach another course Tuesday, Thursday as well, morning, early afternoon. So that limits my schedule somewhat on the same day, but feel free to meet there. And the other thing was the focus tutorials that I offered to have. So if you're really interested in handling some topic, let me know. I'll also try to talk about it. Okay. So this is outdated. That was my bad. So what we're talking about here, let me go to a more recent. It's this one here, right? So apologies, this is I screwed up there in terms of the slide. Okay, so what's expected? Attendance and participation. This is reading papers, but this is actually videos. There's going to be some modeling exercises. I say 2 there. There's going to be more than that, and then a project guidance. Most of these modeling exercises can be done in class, but we'll see. And then the project is involved as well. This is required. Interdisciplinary teams are encouraged. They're actually not required. I will ask for end-of-term presentation from people. So we're going to be pursuing projects. A lot of that pursuing will be in class, and people will no doubt become aware of kind of what's kind of going on and what projects there are. But at the end of the term, I'd like to see some things in the presentation that describe. And I'm trying to remember here. Yeah, I don't describe the presentation, but in the syllabus I talk a little bit about what's involved. And the syllabus is posted to Moodle right now, which is the course site. So for those not familiar with it, CS uses a system known as Moodle, and if you go to Moodle, moodle.cs.usask.ca, you'll be able to find. You should be able to find APTA. If you can't, maybe because you're not registered in the course. If you are registered, you should be able to see it. Let me know if you can't. See if I can get someone to correct that. Okay. So if you go to Moodle, there's a syllabus there. Syllabus has some specifications for what I expect with a project. Briefly speaking, what I'm looking for in a project is something that will involve going the breadth of the modeling process, in the sense that you build a model. Sometimes students have gone to a paper and built a version of the model that's already described. Many other students have built up models from scratch. Once we build a model, the model needs to be thought through what it includes, so I'm looking for some specification according to a vision that you'll be soon encountering of what's in the scope of the model. That's so-called endogenous, exogenous, ignored. Those are 3 topics you'll find in the video I'll be asking you to view. And you'll be asked to, as well, test that model out some. Test how it behaves, look at the plausibility of its behavior, test it under different assumptions. So change this assumption, change that assumption. How radically different is its behavior? Does that make sense when you change the assumption that you're seeing this sort of change, or is it a thing that's implausible? So that's so-called sensitivity analysis. There may be some components called calibration, which we'll be covering. Then you'll need to use the model in some scenarios. What do I mean by scenario? You'll ask what-if questions with the model. Say, well, what if we did this? What if we did that? If we're dealing with computer systems, and we're interested in simulating how does a computer system function under large numbers of hits to a small number of videos at the same time. That's the sort of thing you can simulate. Another thing relevant to CS would be how would the productivity of a software development team differ if you were to bring new people on board when it was having quality assurance problems? Or if you were to institute agile development processes to replace, sort of classic so-called waterfall development. If you were to change things in that way, or if you were to provide extra incentives for bug finding, you might be able to capture that in a model that would simulate other people in the project. At the biomedical level, this might be used. Model simulating behavior of a cell, or simulating behavior of a human heart. In the electrical simulation, mechanics of it, or what have you. Here we're talking about running scenarios that ask what if in the normal scenario. Maybe last year someone did a simulation of epithelial cells in the esophagus with the idea of understanding how flu affects them. So you might ask, well, what if they were infected by flu? How would that change the behavior over time? Or you might ask, if we could have this diabetic monitor their blood sugar very frequently, say every 30 seconds with an automatic meter, and give them insulin little bits, how would that stabilize their blood sugar levels over time? These are the sort of what-if scenarios you might ask with your model. So you run it kind of in baseline with no change, and then you ask different what-if and compare the results. So I'm going to be asking for that, for example. This has to be documented in a way that's understandable and sort of comment on as to how the scenarios differ. Those are the sort of things you might expect in an end-of-term presentation, like shoot for. Other people might be working with models that are rather different, and maybe they're recreating an existing model and then extending it, and your emphasis might be different, but I would expect it to include the basic. Okay. So that's something that's expected of you for those elements. Okay, I mentioned interactive student exercises that are going to be occurring in class. How many people here have access to a laptop? Okay, I think pretty much everyone. I'm going to make the request of you bringing the laptop to class. Okay, we'll get you software installed on it. I'll provide you the links this weekend so you can install both sets of software. So-called Vensim, which is a dynamic simulation modeling tool based on system dynamics, and secondly, a second dynamic simulation tool called AnyLogic, which actually supports system dynamics, supports agent-based modeling, and discrete event modeling. And I'll ask you to install both of them. Download them, install them. AnyLogic will probably take a little bit of time to get fully operational, just because it requires something, but you'll probably be able to do it by the next time we meet if you start sooner. And I'd ask you to install that on your laptop. I'd like you to bring the laptop to class, and we'll be providing example models for some of the exercises. For some exercises, we'll build it up from scratch together here in class. So if your laptop is problematic, you're not sure you want to use it, and that's fine. Well, we could have a laptop delivered. So we have a thing called the mobile lab, which goes around. They have 30, I think, maybe. So they can provide a laptop for anyone who needs one. Okay? So please, starting next time, bring your laptop, and as soon as you see my request to download software, please do that. The software will be at no cost to yourselves. We have a site license for one case, and the other case is free. But it will be form an important component of the course. Okay. Yes. Okay. In fact, these are the downloads. Yeah. Let's. Problem is, this is. Yeah. I don't know. It's a strange thing. Some of these slides are also outdated. So. Okay. Let's talk about this. Okay. So. Yes. This is right after class. So Tuesday and Thursday after class. Okay. And as I said, the course website is at Moodle. Okay. I'll be posting these things to Moodle. So once you get access to that, you should be able to get all the slides. In fact, I think I'm going to post all the slides for the entire course to Moodle, bearing in mind that you can be able to see them when you go watch the videos. But this will let you kind of see all the slides ahead of time. Bear in mind, I'm not planning to cover them all in course. I'm planning to use the course for the flipped classroom experience. But any of them, if you ask questions, I'll show them, and I can get them. So the two pieces of software, Vensim and AnyLogic. Okay. So those are some comments in the course. In the syllabus, I have some comments on breakdown of marks. The basic gist of it, and I kick myself for not having the slide right here. But the basic gist of it is we have marks for the project, which are the biggest set of marks. And then we have marks for some exercises, some assignments, which you'll be asked to do as part of the course as well. And then there's some marks for participation. Participation will take place in several ways. It can take place here, no question. It can take place by interactions with me and office hours. It can also take place in the form of sort of in the context of the meetings for the flipped classroom experience. You know, being particularly active and engaged in that. It doesn't have to be just questions in lecture form, but also meeting up. So if you're taking a lead role in the project and asking questions in that capacity and so on, that's great. So those are the components of marking. The scheme is laid out there, as I recall in the syllabus. Okay. So any questions about the course right now before we go into motivation? No questions? Okay. So grab me after class if you want to ask a question by whispering. But otherwise, we'll proceed here. Oh yeah, there is one other thing. So some of you may notice at the beginning,